3, 2, 1. All right, so now we're going to get into what we call colligative properties, meaning properties of solutions that will change the original physical properties of the solvent. And it depends upon the concentration of the solute as to how much it changes. A good example is boiling water. Now we already know that water boils at 100 degrees Celsius. And to understand how that works, we'll take a beaker of water and then you put a flame under it, like so, and we're heating this thing up. And then, again, going back to the kinetic theory of gases, when you heat up a substance, whether it's liquid, solid, or gas, whatever, the particles start moving. Well, in this case here, if they move fast enough, they start to break apart from the water. Now, water, again, is polar, which means it has positive and negative parts to it. This side is slightly positive, and this side is this part is slightly negative. And these are what we call lowercase deltas. I mean, kind of positive, kind of negative. But other waters are going to line themselves such that the positive part of water will bond to the negative part of the other water. So it looks something like this. This is a little attachment here. We call these hydrogen bonds, and actually there's one hydrogen bond to that. Whatever. You know, you get this web-like thing going on here. And it keeps going on and on, up, down, left, right, front, back. That's how water bonds to each other. But if you start to heat it up, these things start to vibrate to the point where the bond is broken right here. And this comes off as free H2O gas. So we have H2O particles breaking apart from the pack, if you will. And this is normally a liquid, so we call this water vapor. A gas that is normally a liquid or solid beforehand is called a vapor. So this is water vapor coming off. And there's a certain amount of pressure being exerted by the hotter it gets, the more water vapor that comes off, the more water vapor pressure taking place. And that's how they define boiling point. As being the pressure of the water coming off of a liquid equals the atmospheric pressure, what we call air pressure, whatever temperature that occurs at, that is called the boiling point. It's not because you get a bunch of little bubbles, that is symptomatic of the heat that you're adding to this, but it's the fact that you get to this point right here where the amount of pressure being exerted by the water vapor coming off is the same as the pressure of the atmosphere smacking down the water vapor back towards the liquid area. So this is vapor pressure, and when it equals air pressure, we have the boiling point. So let's suppose now we take another beaker of water, and now we have, let's say, some kind of covalent compound bonding to it. Let's say CONH2 or something like that. This was the first organic compound that was ever synthesized in a lab. It's a big deal. It's a polar compound because it is oxygen and the nitrogen both, for that matter. So water is going to bond to this here and this here. And because there's two of them, you got two waters bonding to this. And then you have a series of other waters bonding to all that. And then you got a bunch of water here that is now more tightly bound to it than it was to the other waters, so that when you now heat this up, isn't that a wonderful candle? I mean, I am so proud. No, I'm not proud of myself. I flunked finger painting in kindergarten. It messed my life up. Anyway, the water's not going to come off as quickly as it did up here. Okay? Why? Because now it's spending a lot of energy with this new bond that it has created. So what's going to happen here is that there's going to be less water coming off of here. And the more stuff you have in, the more solute you have in there, the less water vapor that is going to come off of this. So that means it's going to be less pressure of the vapor, or vapor pressure. Now, since the definition of boiling point is where the pressure of the water equals the pressure of the air in this particular situation, then this means that this is going to take longer to attain air pressure, which means the boiling point increases. So the more stuff you dumped into the water, the longer it's going to take to get the water to get to the boiling point, which is why if you're in a hurry to make macaroni and cheese on a stovetop, not a microwave, because that's cheating, then you're going to have to put the salt in after the water is boiling. Dump it in there and then put the macaroni and cheese in there. Don't do it beforehand because it'll take longer to get there. And you might be late for the bus or whatever it is you're trying to get to, the concert or whatever. So, there is a mathematical equation that makes that relationship, and that is the following. The boiling point of a substance is equal to the original boiling point, and since it's going to go up, we're going to add to that, this is the original, that's what the O stands for, plus a correction factor, and that is what we call the KB, and this is literally called the boiling point elevation constant. So, that's kind of a cool name for a constant because it's telling you exactly what it's used for. I would have thought of having a name like James constant or something. Whoever discovered this first, I just like the name James. Times, and here's where the amount of solute comes into play, the molality of the solution. Now, for every solvent, you have a different KB. For water, this is equal to 0.510 degrees Celsius per mole per kilogram. Yeah, again, it's a constant, so labels don't make sense for constants. It's kind of there as part of a graphing thing that they do, and that's what you come up with. Nobody really cares. Outside, they want to make sure that the labels cancel out, and you're left with degrees Celsius when the molality cancels out there. You will not have to memorize this number. I will give you this to you on the test, just like its counterpoint, which we'll talk about just a little bit. Okay? So, let's take a look at the practice problem that I have given you for this. We want to know the boiling point for an acetone solution. Now, we're just going to say acetone's a liquid, it's a volatile liquid, and this is not exactly correct, but we're going to pretend like it is. So it's a 2.50 mole per kilogram acetone solution. So, let's take a look at that. So, the boiling point, I'm going to write this again, equals the original boiling point plus the correction factor of KB times the molality. Okay? So the original boiling point of water is 100 degrees Celsius plus KB, like I said, is 0.510 degrees Celsius per mole per kilogram times the molality. The molality of the problem is 2.50 moles per kilogram. Okay? So I punched that out my calculator, rounded off the three significant figures, and my answer is 101 degrees Celsius. So the boiling point will increase by a degree. Okay? So that's how we can calculate the new boiling point when you add stuff to it. Like I said, this is called boiling point and increasing or elevation and freezing point depression.